In this fourth and final video of the Neuron Action Potential series, I am going to go over how myelin sheath work. Many neurons in the central and peripheral nervous system are what are called myelinated neurons. The neuron in this image is a myelinated neuron. What that means is it has multiple sections of myelin sheath that exist on its axon. Each one of those that I highlighted in black is a section of myelin sheath. If you look closely at one section of myelin sheath, it looks like the rings of a tree. You have these concentric layers that exist around the axon. In reality, those are not separate layers. What myelin sheath is it's one continuous piece of fat. It's made up of lipids. And what that piece of fat does is it wraps around the axon continuously and thus forms these concentric layers. So each section of myelin sheath is mostly a piece of fat that is wrapped around the axon continuously. In the central nervous system, myelin sheaths are created by oligodendrocytes. In the peripheral nervous system, myelin sheaths are created by Schwann cells. No matter which cell type creates the myelin sheath, structurally they all are identical. And functionally, what myelin sheath allows for is for neurons to propagate faster action potentials. Another way of saying that is myelin sheath allows for the conduction velocity of action potentials to increase. And the way that they do that is that they allow for a process which is called saltatory conduction. And that is what we are going to take a look at now. If you look at a myelinated neuron, you will notice that throughout its axon, there is not one continuous section of myelin sheath. Myelin sheath does not exist around an axon in the way that insulation exists around a pipe. Instead, there are sections of myelin sheath, and between those sections, there are gaps. And what those gaps are exposed areas of the axon. If you look at an entire myelinated neuron, what you see is a section of myelin sheath, and then an exposed portion of the axon. And then you see another section of myelin sheath, and then an exposed portion of the axon. And this just continues down the entire length of the axon. Those exposed portions of the axon are called the nodes of Ranvier. Or if you were to just look at one of them, it would be called the node of Ranvier. To be able to fully comprehend why myelinated neurons are organized this way, what we need to do first is actually look at a non-myelinated neuron and do a bit of a thought experiment. Before we get into that thought experiment, and in order for that thought experiment to make any sense, there are some videos I would highly recommend you watch if you haven't already. Definitely, I would watch the resting membrane potential lecture if you are not familiar with how the resting membrane potential develops. Nobody is understanding truly how myelin sheath works if they don't understand the resting membrane potential. Additionally, Watching the first lecture in this 4-part series over the action potential is also very important. If you don't understand how an action potential is generated and propagated, understanding how myelin sheath work is really impossible. I will try to link these on the screen, although depending upon the device you're on, it doesn't always show up for me. But I will most certainly link each one of these videos in the description as well. You can also find them on my channel. I very well could be wrong, but I think if you really want to know this material, then I'm pretty certain you'll be happy that you did this, meaning you watched these 2 videos. All right, let's get back to saltatory conduction. So let's pretend that we have a non-myelinated neuron. Non-myelinated neuron implying that there are no sections of myelin sheath throughout the axon. There's still an axon hillock, and within the axon hillock there are voltage-gated sodium channels. Throughout the axon hillock's plasma membrane, there are voltage-gated sodium channels, but throughout the plasma membrane of the axon, there are no voltage-gated sodium channels. We're taking all of those away. So no voltage-gated sodium channels in the plasma membrane all throughout the axon, only voltage-gated sodium channels in the membrane of the hillock. Okay, throughout the hillock and throughout the axon, the resting membrane potential would still be -70 everywhere. Okay? And we can still depolarize the hillock region to threshold, to -55 millivolts. As long as we get enough graded potentials and thus sodium from the dendritic regions into the hillock region, then we can depolarize it from -70 to -55 millivolts. If we do that, then the voltage-gated sodium channels within the membrane of the hillock will open up, and we know that sodium will shoot in through its chemical and electrical driving force and drive the interior of the hillock from -55 millivolts to +30 millivolts. This is what usually would be referred to as generation of an action potential. However, as you're about to see, on a semantic level, we can't really call this an action potential anymore because of what's about to happen. Right next to the hillock region, there is this first region of the axon, which is still -70. So this big depolarization, that's usually referred to as an action potential, is going to move into the next negative area, which is within the axon, first axon region that lies next to the hillock. And as this big positive impulse, this depolarization, moves into this negative region of the axon, it is going to depolarize that region, because that region is going to gain a whole bunch of positively charged sodium ions. So, of course, it's going to depolarize. Now, how much it depolarizes is not the relevant part just yet. What would happen here is, without voltage-gated sodium channels throughout the plasma membrane of the axon, what's going to happen to this signal is it's going to decrement as it moves away from the point of origin. So as this depolarization moves away from the axon hillock region into the first region of the axon and to the next and to the next, the signal is just going to keep falling apart. It's going to keep decrementing. It's going to keep becoming more and more and more negative, closer to the resting membrane potential. This is going to happen because of the fact that voltage-gated sodium channels don't exist in every region of the axon's plasma membrane. They don't just keep opening up and allowing for sodium to come in. Because what would usually happen is this depolarization would move into the first negative region of the axon, depolarize it, and then voltage-gated sodium channels would open up, sodium would shoot in, drive the interior in that region up to positive 30. But those voltage-gated sodium channels aren't there, right? So as this signal moves from one region to the next, it just falls apart. It decrements more and more and more because the voltage-gated sodium channels that are in the plasma membrane that usually open up and recharge the signal, they're not there. So what you're actually looking at right now is a graded potential. If there were only voltage-gated sodium channels that existed in the axon hillock and nowhere else throughout the plasma membrane of the axon, then what would truly be generated, this is somewhat of a semantical argument, but what would really be generated here is a graded potential. Because as it moves away from the point of origin, meaning the axon hillock region, it would fall apart. Now the question becomes, why would it fall apart? Right? Why, when you remove the voltage-gated sodium channels from the plasma membrane of the axon, would this signal decrement as it moves along the axon? Why would it essentially become a graded potential? So let's just say, again, this first region of the axon is negative 70, and this big depolarization moves from the hillock region into the first region of the axon, and let's just say that it depolarizes it to positive 30. How much it actually does, yet again, is really not all that important. It would just make this region very positive. Usually, as I've said, this would open up voltage-gated sodium channels. Would have done it much sooner than this when it got to like negative 55, but usually voltage-gated sodium channels would have opened up in this region, but they're not there, so they couldn't have opened up. So what would happen? If you make the interior positive 30 millivolts, that's going to have an effect on sodium and potassium. What do we know about potassium? Potassium is high inside of the axon, all throughout the neuron, and it's low outside of the axon in the interstitial fluid. What do we know about sodium? Sodium is high outside of the axon in the interstitial fluid, and it is low inside of the axon in the intracellular fluid, or the cytosol. Well, we've made the interior positive 30 millivolts. So let's start off thinking about what effect that would have on potassium. If we make the interior positive 30 millivolts, the interior is usually at the resting membrane potential negative 70, but now we've made it positive 30. Okay? Negative 70 millivolts on the interior, what effect does that usually have on potassium? It's a strong negative electrical driving force that pulls the potassium ions backwards, and it slows down the rate at which potassium can leave. But what is the interior right now? It's positive 30. So by making the interior positive 30, the entire negative electrical driving force that pulls potassium ions backwards and slows down the rate at which they can leave is gone. So what's going to happen is potassium now is going to increase the rate at which it leaves through its leak channels. Of course it is, because if, again, the interior doesn't have a negative electrical driving force pulling it back anymore, then potassium can increase the rate at which it leaves. If somebody was pulling on you with a bungee cord and slowing down the rate at which you were running away from them, and then all of a sudden the bungee cord was cut and they weren't tugging on you anymore, of course, the speed or the rate at which you could run away from them would increase. The same thing here. We remove that negative electrical driving force by depolarizing this region of the axon and making that region positive, then all of a sudden, there's nothing in terms of a negative electrical driving force pulling the potassium ions backwards anymore, and they can increase the rate at which they leave. What about for sodium? Usually the interior is negative 70. Yet again, that's a negative electrical driving force, and that allows for sodium to come in through its leak channels via an accelerated rate. That negative electrical driving force helps increase the rate at which sodium can enter. But now we've depolarized this region to positive 30, so that negative electrical driving force pulling the sodium ions in is gone. So thus the rate at which sodium is going to come in, if the interior is positive 30 millivolts, is going to be decreased. So depolarizing this region of the axon to positive 30 is going to have effects on both potassium and sodium. It's going to increase the rate at which potassium can leave because there's no negative electrical driving force pulling it backwards anymore, slowing down the rate at which it can leave. And it's going to decrease the rate at which sodium can enter because, yet again, we removed the negative electrical driving force, which was helping pull the sodium ions inward. So what's going to happen if all of a sudden we depolarize this region and now potassium can leave at an increased rate and sodium is coming in at a decreased rate? What is going to happen is, if this region of the axon is positive 30 and potassium is leaving at a greater rate than sodium is coming in, then we can apply some concepts from the resting membrane potential. If the interior is losing more positively charged ions than it's gaining, right? It's losing more potassium than it's gaining in sodium. Then the proportion of negatively charged ions on the inside is going to be rising compared to the proportion of negatively charged ions on the inside, because the inside is actively losing positively charged ions. Thus, the inside is going to begin to become more negative. In essence, the interior is repolarizing to some degree. How much more negative it becomes exactly? Well, I don't know exactly for this conversation, but let's say that it drops by 20 millivolts. Right? It becomes 20 millivolts more negative. And this is all due to the fact that more potassium is leaving than sodium is coming in, driving the interior back down to a more negative value. There are some other factors that would be contributing to this as well, but they're not quite as relevant for myelin sheath. One, there would be sodium-potassium pumps working, and the way that sodium-potassium pumps work is they take 3 sodium ions and they pump 3 sodium ions out for every 2 potassium ions that they kick in. The big thing to recognize is, well, the depolarization is made up of sodium ions, and the sodium-potassium pumps would be kicking sodium ions out. They become a lot more active when sodium comes into the cell. So simply the removal of sodium ions would cause the interior to become a little more negative as well. Additionally, since the sodium-potassium pumps kick 3 positively charged ions out and only take 2 in, the more active they are, the more negative they make the interior, because sodium-potassium pumps kick more positively charged ions out than they return, and that drives the interior down to a little bit more of a negative value as well. Additionally, as the depolarization moves along the axon and it keeps going into these negative regions, the sodium ions just kind of become a little bit more dispersed throughout the fluid, and that's going to have an influence over how depolarized it would become in subsequent regions. But the big thing I want you to recognize is this, at least as it relates to myelin sheath. The big reason that the signal is going to decrement, right, become more negative, fall apart, is because as each region of the axon becomes depolarized, that's going to allow for potassium to leave at a greater rate than sodium will come in through the leak channels, and that's going to cause the cell to lose more positively charged potassium ions than it gains in positively charged sodium ions. So all these factors play a role, but this is the big one. And what's going to happen next? Well, the next region would still be negative 70. So clearly, this region of the axon, being positive 10, is a lot more positive than the region that lies next to it. It's going to go into this next region, and it's going to depolarize that region. Exactly how much it depolarizes it, again, not entirely relevant, but just to stick with what we were doing, this is not going to happen exactly like this, of course, not to this degree, but let's just say it depolarizes it to positive 10. What's going to happen in this region? Well, yet again, what did we do to this region? We depolarized it by 80 millivolts. We totally removed the negative electrical driving force within this region. So now potassium is going to leave from this region at a greater rate than sodium is going to come in. And as potassium leaves at a greater rate than sodium enters, this region is again losing more positively charged ions than it's gaining. So the interior is going to begin to become negative. Let's say that it goes down to negative 20. I don't know. It repolarizes by 30 more millivolts. Becomes 30 millivolts more negative. And again, some other factors will play a role in this as well as to why this kind of decrementation happens. But what's still going to happen to this wave, right? This depolarization. It's negative 20 in this region of the axon, and in the next region, it's negative 70. Right? So this region where it's negative 20, that's 50 millivolts more positive than the region where it's negative 70. So it's going to move into that next region. And let's say that it makes that next region negative 20, just to stick with what we've been doing. Okay? That's still depolarizing that region. Compared to negative 70, that's 50 millivolts more positive. So yet again, yes, there is a negative electrical driving force to some degree in this region, but it's not as strong. So still, potassium is going to be able to leave at a greater rate than sodium is going to be able to come in, because we're not at the resting membrane potential. At negative 70, potassium leaves at the same rate that sodium enters. But if we're at negative 20, that is a weaker negative electrical driving force, and now potassium can exit the cell at a greater rate than sodium can enter. There's not as strong of a negative electrical driving force pulling potassium back or sodium in. So since potassium leaves at a greater rate than sodium enters, yet again, this region would keep repolarizing, right? It would keep becoming more negative. And let's say that it goes down to negative 40. I think you get it at this point, or I hope you do. As this signal moves down, this depolarization moves down the axon, it's just going to keep falling apart. This is a graded potential. This is, again, somewhat of a semantical argument, but an action potential, by definition, is supposed to be non-decremental. That means in order for something to be an action potential, in every region of the axon, it needs to be positive 30, positive 30, positive 30, positive 30. And that's really a product of the voltage-gated sodium channels existing throughout the plasma membrane of the entire axon. It keeps recharging that signal, that electrical impulse, and it makes it non-decremental, which is what an action potential is. This can't be an action potential. If there were only voltage-gated sodium channels in the axon hillock and nowhere else throughout the axon, what would be generated at the axon hillock would be, people could argue this to some degree, but it would be a graded potential ultimately. And what effect would this have on the neuron? If there's only voltage-gated sodium channels in the hillock, the plasma membrane of the hillock, but nowhere else throughout the axon, then what's going to happen is, yes, the hillock will depolarize to positive 30 millivolts, but as this big depolarization travels down the axon, it's going to decrement. It's just going to keep falling apart due to the fact that more potassium is leaving than sodium is coming in. Major factor. So every region will become less and less positive, or more and more negative. Every region will repolarize to some degree. As I did here, it was like positive 10, and then I went to here, and it was negative 20, and then we were at negative 40. So if this were to keep happening, what do you think would occur by the time that we got to the axon terminal buttons? The answer is nothing. There would be no electrical impulse left. And if there was, it'd be totally insignificant. Maybe by the time that we got into the axon terminal button, inside of the button, there may be enough of a depolarization left that the interior would get to, like, negative 65 from negative 70. That's not enough to open the voltage-gated calcium channels within the plasma membrane of the buttons. And if the voltage-gated calcium channels don't open, then excitatory or inhibitory neurotransmitters are not going to be released from the axon terminal buttons, or whatever variety of neurotransmitter they are. It doesn't matter. Neurotransmitters aren't going to be released, period. If you cannot depolarize the axon terminal buttons to get them to threshold to the point that the voltage-gated calcium channels within their membranes will open, then there will be no influx of calcium, and the neuron simply will not release neurotransmitters. It won't be able to do its job. Most likely, there will just be no impulse left by the time that it reaches the buttons. So the buttons will just be stuck at negative 70, and the neuron has completely lost its function. The job of this neuron is to generate and propagate action potentials. It can't do it without having voltage-gated sodium channels lining the entire length of the plasma membrane, because those voltage-gated sodium channels are what ensure that every region becomes positive 30, positive 30, positive 30, right? It recharges the voltage or the impulse to ensure that by the time that it gets into the hillock, right, that impulse is strong enough, positive enough, that it'll depolarize the axon terminal button region to a threshold level so that the voltage-gated calcium channels will open, calcium will spill in, and you will get exocytosis of neurotransmitters. The point of showing you this, which is a non-myelinated neuron, and showing you what would happen if it didn't have voltage-gated sodium channels all throughout the plasma membrane of its axon, and thus trying to drive home the point why it does have voltage-gated sodium channels throughout the entire length of its plasma membrane. The point of all of this is to make sense of how myelin sheath allows for neurons to propagate faster action potentials. I don't think there's any way to understand myelin sheath and saltatory conduction without first understanding why non-myelinated neurons are organized in the way they are. So now I think we can do it. We can look at a myelinated neuron like this, and we can see and understand how the neuron being myelinated allows it to propagate action potentials down its axon at faster velocities. That process being called saltatory conduction. So let's go ahead and do that. So here is the axon, and this time we are going to put sections of myelin sheath around portions of the axon. All right, those are sections of myelin sheath. Yet again, there are sections of it, and in between the sections, there are gaps where the axon is actually exposed. So to start off with, within the hillock here, we still have all these voltage-gated sodium channels. All throughout the hillock and the axon, it is negative 70 millivolts everywhere. If we can depolarize the hillock to threshold, we know what happens. We get to negative 55, the voltage-gated sodium channels open, sodium shoots in and drives the interior to positive 30 millivolts. And what's going to happen is now this big depolarization, which is going to be an action potential because it's going to be non-decremental, is going to begin to move down the axon, right? This area of positivity is going to be pulled towards the next area of negativity, which means it's going to be pulled down the axon, where it is still negative 70. Now, the first fun part of this is, the first part of this that's, fun to discuss is underneath where the myelin sheath is wrapped around the axon. There are very, very few, if any, voltage-gated sodium channels embedded into the plasma membrane of the axon. They're basically non-existent. So as this depolarization moves down the axon, Right now, it's moving down the portion of the axon that's wrapped in a section of myelin sheath, and embedded into the plasma membrane of the axon, there are no voltage-gated sodium channels. They are not here, right? They don't exist to any meaningful degree, at least. And the logical question to that would be, doesn't the signal decrement then? Right? If there's no voltage-gated sodium channels in the plasma membrane of the axon underneath where the myelin sheath exists, then there's nothing there to recharge the signal. Right? So doesn't potassium leave at a greater rate than sodium comes in, and thus the interior repolarizes to some degree, becomes more negative? The answer to that is no. You don't need voltage-gated sodium channels to exist in the plasma membrane of the axon that is wrapped in myelin sheath. And the answer to that is it prevents the potassium from being able to leave. What it does to sodium is irrelevant because there's a ton of sodium, theoretically, that exists inside of the axon here that's driving the interior up to positive 30 millivolts. The main thing that we want is not to lose any positively charged potassium ions, because that would drive the interior back down. If potassium were able to follow its chemical driving force out of the plasma membrane, it would start leaving at an accelerated rate. And the loss of positively charged potassium ions would decrease the number of positively charged ions inside as a whole and increase proportionally the number of negatively charged ions, and that would make the interior more negative. But that's not going to happen because myelin sheath, maybe you've heard this before, it insulates the axon. What that means, most importantly, is it prevents the leakage of potassium ions. And thus, it prevents this signal from repolarizing, or also said, it prevents the signal from decrementing. So the signal can stay at more or less positive 30 millivolts the entire distance that it travels down the axon that is wrapped in myelin sheath, because it prevents the loss of those positively charged potassium ions, and thus prevents the interior from becoming more negative, so that the interior can stay more or less at positive 30 millivolts and continue to travel down the axon. So the next logical question is, what's the point of the nodes of Ranvier? Right? Remember, there's a section of myelin sheath, then there's another section, and in between those two sections here, there's an exposed portion of the axon, which is called the node of Ranvier. Why is it there? Insulation is never perfect. For anyone that's ever lived in a building with insulation, they know that this is true. You insulate a house in the wintertime to prevent hot air from going out. You insulate a house in the summertime for the purpose of cool air not going out. You insulate the axon of a neuron with myelin sheath for the purpose of preventing particularly potassium ions from being able to go out. But none of it is perfect. Again, if you've lived in a house with insulation, you know that even in the wintertime, where the house is insulated and it's supposed to prevent the heat from going out, it can do a pretty good job of it. But over time, it still lets some heat out. And the same thing is true for myelin sheath. Over a distance, it still does let some potassium ions out. Even if it's not a lot, some potassium ions do manage to sneak their way out, and that means that the interior does decrement to some degree. As the depolarization moves down the axon, through the portion of the axon that's wrapped in myelin sheath, the signal stays pretty strong. It stays around positive 30 millivolts, but it does decrement some because insulation is not perfect. Myelin sheath is not perfect. Or better said, myelin sheath are not perfect. So this is the explanation as to why you can't just wrap the entire axon of a neuron in myelin sheath. You can't just have one piece of myelin sheath wrap around the entire axon, because the signal still does decrement some as it moves down the axon. There's no way around it. So if you were to just myelinate the entire axon, the whole thing, no nodes of RON-VA, the whole axon is wrapped in myelin sheath, you would run quite a risk in that by the time the impulse got to the level of like the buttons, it would have decremented enough that it may not be able to depolarize the buttons to the point where the voltage-gated calcium channels would be able to open and no neurotransmitters would be released, and the neuron, of course, would not be able to do its job. So instead, we have these gaps that exist between sections of myelin sheath. Right, here's a section of myelin sheath and another section of myelin sheath, and in between the two, we have this exposed section of the axon, and we call that section the node of RON-VA, and within the node of RON-VA, within the plasma membrane of the exposed axon, there's a very high density of voltage-gated sodium channels. So in the nodes of RON-VA, we find a high concentration of voltage-gated sodium channels in the axon's plasma membrane. Remember, that's an exposed portion of the axon. The node of RON-VA is. So inside of the node of RON-VA, presumably, it would be negative 70 millivolts. And as this, what is action potential, big depolarization, moves down the axon through the section that is myelinated, right? Has a section of myelin sheath around it, preventing the loss of potassium ions and thus preventing very much decrementation from happening, right? Not very much decrementation occurs. The signal stays pretty stable, but does decrement a little bit. Let's say that it goes down to positive 20, positive 25, I don't know. By the time that it gets into the section of the axon that is the node of RON-VA, this portion of the axon that's exposed between two sections of myelin sheath, it's going to easily depolarize that region to a threshold level, which is negative 55 millivolts, and all of these voltage-gated sodium channels are going to open up within the plasma membrane of the node of RON-VA, this exposed portion of the axon. And thus, sodium will shoot in and drive the interior of the node of RON-VA up to positive 30 millivolts again. We are recharging the action potential or the impulse here. And that's ensuring that the interior stays depolarized all the way to positive 30 millivolts. Perfect. And now what's going to happen is this big depolarization, this action potential, is going to continue traveling down the axon where it's still negative 70 millivolts, and it's going to travel through a portion of the axon that's wrapped in a section of myelin sheath. And that section, right, is going to become positive 30 millivolts as the action potential sort of moves into this section and depolarizes it. But since this section of the axon is wrapped in myelin sheath, very little potassium ions are going to be lost. So as the impulse travels through this section of the axon that's wrapped in myelin sheath, it's not going to decrement much. It's going to stay right around positive 30. Let's see, again, maybe it goes down to positive 25, positive 20, I don't know. It decrements some, but not very much. But now it's going to enter into another section of the axon where it's still negative 70. And this section of the axon is what is known as another node of RON-VA. It exists between two sections of myelin sheath, and it is an exposed section of the axon. And again, this region will easily get depolarized to threshold of negative 55 millivolts by the action potential depolarization that's heading into it, and that's going to cause the voltage-gated sodium channels within this node, within the plasma membrane of this node of RON-VA to open up. sodium is going to shoot in, and it's going to drive the interior of this node of Ranvier up to positive 30 millivolts. Yet again, we've recharged the signal again. And now the same exact thing is going to happen over and over and over and over and over again down the length of the axon. As the action potential travels through the portions of the axon that are wrapped in myelin sheath, it will decrement very, very, very little because it's so insulated, and the loss of ions, particularly potassium ions, is so heavily reduced. That ensures the signal does not decrement, but it does decrement some. So as it continues traveling on towards the next region of the axon, that next negative region of the axon is going to be a node of Ranvier, an exposed portion of the axon. And it will depolarize that region to threshold, and in the plasma membranes of the nodes of Ranvier, there are a lot of voltage-gated sodium channels. So they will open up, sodium will shoot in, recharge the signal, and then the signal can keep traveling down the axon and go through the next section of the axon that's wrapped in myelin sheath and not decrement very much, but a little bit it will. So then it goes into the next node of Ranvier and the signal gets recharged. This whole process is referred to in scientific terms as saltatory conduction. The movement of the action potential from one node of Ranvier to the next, to the next, to the next, to the next, to the next. That is the term that it is given. Saltatory conduction is a process, and it's a process of how the action potential propagates down a myelinated neuron's axon. So this is the sort of image you always see in textbooks. This is a node of Ranvier. And presumably, what happened is a action potential, this big depolarization, went into this node of Ranvier, depolarized it easily to threshold. That caused voltage-gated sodium channels within its plasma membrane to open up. Sodium shot in to this particular node of Ranvier and made it positive, 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 right? Made the whole interior positive. What that really means is the interior became positive 30 millivolts. And then the action potential continued to travel down the axon. And it traveled into another portion of the axon that is wrapped in myelin sheath, right here, wrapped in a section of myelin sheath. And as the action potential travels into this section, it can maintain its charge of around positive 30 millivolts very, very well. Right? The signal doesn't decrement very much because the myelin sheath insulates this particular part of the axon. It prevents any real meaningful leakage of positively charged, especially potassium ions. And that ensures the signal doesn't decrement much, but it may decrement a little bit. So then by the time that the action potential moves into the next section of the axon, which happens to be another node of Ranvier, an exposed section of the axon, it's easily going to depolarize that particular portion of the axon, the node of Ranvier, to threshold, and more voltage-gated sodium channels are going to open up in the plasma membrane of this node of Ranvier. Sodium is going to shoot in, the interior is going to be driven up to positive 30, and the action potential is going to keep propagating down the axon, and the process will repeat. This whole process, again, in scientific terms, is referred to as saltatory conduction. Now, the biggest problem I had was when texts and teachers or whoever would talk about this as if the signal jumps around almost like a rabbit. You always see that in textbooks, discussions, that the saltatory conduction, the action potential, it jumps from node to node to node, which is in my opinion, wildly confusing concept because the signal doesn't jump. I guess if text were to continue on beyond just saying the action potential jumps from node to node to node and explain it, then I guess maybe it would make more sense to use that term. But from my experience, and this was years and years of experience of reading many different textbooks, they almost never do elaborate. So you're left literally believing that, or thinking that somehow an action potential is like jumping outside of the axon to the next node or something. It's total nonsense. What is happening is the action potential propagates down a myelinated axon just like it propagates down a non-myelinated axon, right? It travels down an axon, the action potential of a myelinated axon, just like it travels down a non-myelinated axon. It's the same thing. There's just one difference, and that is when you have a non-myelinated axon, there are voltage-gated sodium channels that line the entire length of the axon's plasma membrane. There has to be, because you have to recharge the signal in every single region to ensure that the signal doesn't decrement too much. So sodium is going to shoot in. It's going to drive the interior of this non-myelinated axon up to positive 30. It's going to go into the next region where it's negative 70. It's going to depolarize that region. So then more voltage-gated sodium channels will open up. Sodium will shoot in, drive the interior yet again to positive 30. This depolarization action potential will move into the next region where it's negative 70 to polarize it, and the same thing will repeat. This is how a non-myelinated neuron's axon functions. You need voltage-gated sodium channels to keep opening up down the entire length of the axon, because otherwise the signal would decrement too much. In the case of a myelinated axon, you don't need voltage-gated sodium channels to be located really in any other region than within the plasma membranes of the nodes of RON-VA, right? The portion of the axon that's exposed. That is, the nodes of RON-VA is where the charge impulse will be recharged every time. You don't need voltage-gated sodium channels to be located in the plasma membranes of the axons. You don't need voltage-gated sodium channels to be located in the plasma membrane of the axon that is wrapped in myelin sheath. It's totally unnecessary, because in that portion, the signal, in that portion of the axon, the signal is not going to decrement. You don't need to recharge the signal in that section. The signal doesn't decrement. So why would you need voltage-gated sodium channels to be located in the plasma membrane of the axon that is wrapped in myelin sheath? You wouldn't. In a myelinated neuron's axon, you're only going to find voltage-gated sodium channels, for the most part, within the plasma membranes, within the plasma membrane of the nodes of RON-VA. Because that's the only portion or portions of the axon where the signal, the impulse, is going to be recharged. So as an action potential propagates down a myelinated neuron's axon via saltatory conduction, the only place that the voltage needs to recharge is within the nodes of RON-VA. Nowhere else does that have to happen, meaning that within the axon, any portion of the axon that lies underneath a section of myelin sheath, there are no voltage-gated sodium channels that exist within the plasma membrane of that portion of the axon, and thus the voltage does not need to be recharged at any point as the action potential travels down that portion of the axon. And what this ultimately allows for, since the voltage only needs to be recharged within the nodes of RON-VA, it allows for incredibly fast action potentials. It allows for what are called action potential conduction velocities to be significantly greater, right? Significantly faster. Compare this to a non-myelinated neuron's axon. The voltage needs to be recharged in every single region of the axon. So in every region of the axon, voltage-gated sodium channels are opening up, allowing for the interior to become positive 30 as sodium comes in. And then in the next region, voltage-gated sodium channels have to open up. Sodium shoots in, drives the interior up to positive 30. Every single region, this process has to repeat over and over and over again. And what it does is it slows down the velocity at which the action potential can propagate. Now compare that to a myelinated neuron, where the voltage only needs to recharge within the nodes of Ranvier, significantly less locations compared to a non-myelinated neuron's axon. So since the voltage only needs to be recharged in very few locations within a myelinated neuron, it can then propagate action potentials at least 100 times faster than a non-myelinated neuron. It's really quite incredible, and that's what this whole process of saltatory conduction allows for. Incredibly fast, high velocity action potentials. So I really hope this video helped you understand how myelinated neurons are able to propagate such fast action potentials, thanks to the fact that they have their axons wrapped in myelin sheath, sections of myelin sheath. Additionally, if there are other videos you would like to see on any material related to human physiology, let me know. And over time, I can assure eventually I will create one for you.